Awesome. Thanks for the introduction, Owen. My name is Michael Kaplan. I'm an engineering manager at Ava Labs, specifically on the platform engineering team. And today, here to talk about the new flows for validator management that were enabled by ACP 77. So to get started, first we want to make sure we're all on the same page as far as what we mean when we say validator management. I think it's a pretty broad term. I think that hopefully most of you here are familiar with this general network architecture for Avalanche, where we have the primary network, including the X, P, and C chains, where all of the validators are registered on the P chain. That's where also a Vox is staked to become a primary network validator. But then we also have all of these L1 chains with their own independent validator sets. And when we talk about validator management, what we're really trying to do is answer these three questions. Who can join the L1 validator set? How do they do so? And why do they do so? The who part traditionally breaks down into either proof of authority or proof of stake, which I'm sure many of you are familiar with. The how part gets into the validator manager contracts that we'll talk about today, and why gets to the incentives as far as validating chains. So I want to first start by taking a step back to what subnet validator management looked like prior to that upgrade, which formally introduced L1s. And like I said, there's two main categories, proof of authority and proof of stake. The proof of authority case for subnets was managed via the owner of the create subnet transaction. This create subnet transaction specifies the P-chain addresses and the thresholds that represent the owner of the subnet, and the owner is able to make unilateral changes to its validator set as far as defining who becomes a validator and who is removed from the validator set. This worked okay for proof of authority chains because it's really just a traditional multi-signature setup. However, it still required those subnet validators to be primary network validators, which required them to stake 2,000 of Vox, had a very high upfront cost. It was not a standard multi-sig wallet management because it's on the P-chain using the P-chain's virtual machine, the platform VM, rather than the EVM where you have multi-sig tools such as safe and whatnot. And finally, it lacked guardrails in terms of making sure that a not too much stake weight would churn over a certain period of time. So if you have a very small validator set and then you instantly add, say, 100 times the total stake weight, that can cause problems for consensus. And those guardrails did not exist on the P-chain. It also, because of the fact that all subnet validators needed to be primary network validators, they were tied to their end time and did not have any continuous validation mechanism. So this already wasn't ideal, but it was relatively sufficient for the proof of authority case. However, for the proof of stake case prior to the Etna upgrade, we really lacked sufficient support for all of the various flows and tools that projects wanted to use in order to build their permissionless chains. So the way that proof of stake subnets worked prior to the Etna upgrade was by Avalanche native token, ANTs. If you've never heard of them, it's because they were rarely ever used. And the way that you transformed your subnet from a proof of authority chain to a proof of stake chain was via this transform subnet transaction that had all of these various parameters. It was, in fact, too big to fit on one slide. And these parameters basically defined the staking mechanism for your proof of stake subnet as far as if you supported delegation, the fees for delegation, the min and max stake, the stake durations, and the emissions curve. But typically when you have something that has all of these parameters and all of these different knobs to turn, what that's an indication of is that it's not generic enough to support any given use case. To support a specific use case, you can always add a new knob, add a new parameter to make kind of the square peg fit in the round hole. However, when we sat back and evaluated how this would be used, it became obvious that it wasn't generic enough to support these arbitrary validator management mechanisms that projects were looking for. And in fact, that's why we saw nobody use this transaction on mainnet. For the 2 years that it was live, not a single project chose to go this route, and it's really why we took a step back with ACP77 and evaluated exactly what projects looking to launch permissionless chains wanted to do and how we could best construct the platform to enable them to do so. So the Avalanche native tokens, just a little bit more on them. The reason why they were so specific and lacked functionality and customizability was that they were created on the X chain and then needed to be moved to the P chain, neither of which are programmable. They are all UTXO-based virtual machines that do not support executing arbitrary contract code. So if you wanted to define your own logic as far as different token types or different rules about who can become a validator, who can't, you unfortunately weren't able to do so. So then ACP77 came around, redefining subnets as L1s, removing the requirement that L1 validators need to be primary network validators, and also completely changing how validator management could work on the P chain. And the way that it works now is via ICM, interchain messaging, which hopefully you all know a little bit about already, but it's the BLS multi-signature-based scheme to allow for interchain communication on Avalanche. And given that we already had this primitive, we wanted to leverage it as best as possible to manage validator sets in a generic way that's agnostic to the actual logic of the validator manager itself. And that was how we came up with the design for ACP77. Wanted to make as few assumptions as possible as far as what projects would want to do with their validator management logic, allowing L1s to define their own contracts for these validator managers, and leverage ICM to authenticate changes to the validator set. And what we mean by that is that the P chain is still the registry of all validators. However, it is not the authentication mechanism defining who can become a validator or not, or what rewards you get for becoming a validator of a given chain. Instead, the P chain just processes messages that specify the node ID, PLS public key, and the weight of a given validator. So it has only the base information needed to represent the registry of the validator set, but doesn't actually define who can become a validator or not. The way that that is now defined is through this convert subnet to L1 transaction. And the most important part I would want to point out here is the chain ID and the address of the validator manager for the L1 that's being created. The chain ID and address represent who the validator manager is for the given L1, in the sense that it identifies the address that is able to send ICM messages to the P chain specifying validators should be added, removed, or modified. Also in this convert subnet to L1TX, we have the initial validators of the chains, or of the L1 when it's converted, and this conversion is authorized by the original subnet owner. Once the subnet is converted, that owner is then completely removed from the flow, and they don't have any special permissions whatsoever. So once you convert your subnet to an L1, then the validator manager specified by the chain ID and address in that transaction is able to send messages, as I mentioned, to register L1 validators. And that's what the register L1 validator transaction is used for. It contains an ICM message, which you can see at the bottom there, that identifies the validator to be added as far as their node ID, BLS key, and the weight that they should have when participating in consensus. What's interesting about this transaction is that not just a validator manager can send it. In fact, anyone can send these transactions on the P chain, but the message itself it must be valid, which means it must have been signed by 67% or more of the weight of the existing weight of the L1, and it must have been sent by the validator manager specified in the convert subnet to L1 transaction. And so the message itself is actually completely agnostic to the validator manager type, whether it's proof of authority, proof of stake, or any other types of validator managers that we could create. But it, like I said, specifies the changes to be made to the validator set on the P-chain. Lastly, we have the set L1 validator wait transaction, which specifies modifications to validators that are already in the validator set, including if you set the wait to 0, that's effectively removing that validator from the L1's validator set on the P-chain. And again, the message here must be sent by the validator manager specified in the convert subnet to L1 transaction, but the transaction itself can be sent by anybody. So now we're in this very nice world where the P-chain can act as a registry of L1 validators and is completely agnostic to the validator manager logic. It offloads that to contracts that are just sending these ICM messages. The contracts then themselves are responsible for defining who's allowed to become a validator and the rewards that they get for doing so. And so while the P-chain can support all of these multitude of programmable use cases via these validator manager contracts, that puts a lot of responsibilities on the L1s and on these contracts to manage all of the complexities of validator management properly, as far as integrating with the P-chain messages to be able to properly send and receive acknowledgement of them back, as far as handling collateral that's locked to become, or for validators to enter the L1 validator set, properly issuing rewards, and many of the other edge cases that can come about when creating proof-of-stake networks. And so a need arose for there to be some standard around the validator manager contracts, and ACP 99 is that standard now. So it was actually the first community-proposed ACP by the Suzaku team and Gautier, who's speaking right after this about the various variants of the ACP 99 contracts. But ACP 99 defines a standard for validator manager Solidity smart contracts to be deployed on any any Avalanche EVM chain. And the any Avalanche EVM chain part here is actually very interesting because the validator manager for a given L1 does not need to live on the L1 itself. It can live on a completely separate chain. And there are trade-offs there to be made as far as ensuring the liveness of your chain, which we can get into later. And the contracts are importantly extensible for custom security modules that specify who can register validators and how to register validators. So we have a reference implementation of these contracts that was audited by Opel and Zeppelin, open sourced in the ICM contracts repo here. But those contracts aren't the only ones that you can build. You can use them and inherit from them to get much of the functionality that you need and then add your custom extensions to it for new types of validator management. But the base contracts themselves already handle all of the P-chain ICM message integrations, which are intricate because not only do you need to send a message to the P-chain when validators are to be registered or modified, but you also need to properly handle the acknowledgement of those messages back from the P-chain in order to know that the changes actually took effect on the P-chain. So ICM messages don't provide any guarantees of delivery, so you need to wait for the receipt of those messages in order to be able to act and be ensured of the fact that they were properly taken action upon. Aside from handling those ICM message integrations, the base contracts also support the proof of authority case, the native token proof of stake case, and the ERC20 token proof of stake case as well. So you can stake any arbitrary ERC20 token or the native EVM token of your chain. We don't recommend staking a Vox as your primary staking mechanism because there's a lot of security issues that can arise with that as far as someone trying to take over a lot of stake weight. But these contracts also help define kind of what all of those best practices are in order to help teams and projects avoid them without even needing to think about it. Finally, for proof of stake, as I'm sure many of you know, you don't want to reward validators who misbehave or are otherwise offline. So we have uptime requirements that can be defined, and then proven via ICM message itself. So the validators actually sign messages attesting to the uptimes of their peers. And you can do delegation via these contracts as well via the set L1 validator weight message. So all of this touches upon the base cases of proof of authority and proof of stake. But looking ahead, the reason why these contracts are so exciting is because they can be extended into arbitrary future implementations with various security modules. So some of those potential ideas are a hybrid proof of authority, proof of stake chain, where say you have 30% of the stake weight that is always controlled by some authority, but then 70% that is defined by a permissionless pool of tokens that get locked up in order to join the validator set. And that way the authority can still have some control to censor transactions maybe, or for various use cases, give themselves elevated permissions while still having a permissionless system otherwise. Validator slot auctions, in this model you would have, say, 100 validators for your chain at all times with equal weights potentially, but then anybody can bid to actually get one of those slots and buy the right to become a validator. This is interesting because the tokens bid or locked in order to become a validator can then be repurposed, either being burned or redistributed to the ecosystem or otherwise. I think an interesting point here is that people then would bid the amount that they think is representative of the value that they get out of becoming a validator and having one of those slots, which counts for any potential MEV gains that they can get by having that control of a percentage of the validator set, rather than having some constant rewards curve that's locked up front and doesn't actually account for any MEV rewards or gains that that validator is getting by being a validator. Then we have NFT staking, credential-gated staking, where maybe you have to have a certain badge that was issued by some authority, but then anyone can still stake. And liquid staking and restaking are also very active areas of development that I think Gautier will touch upon. And what's really great to see about this ACP 99 standard is that it's already being adopted by the community, not just by the Interop team at Avalanche Labs, also the Suzaku team and a number of teams that have already launched proof of stake L1s using these contracts, including Beam and Cockney. So we're really looking forward to the further development of a lot of these ideas across many different L1s and the flexibilities that the standard provides for the given project to build their validator management custom to their requirements. So yeah, we're excited for how far that we've come since the launch of subnets, around the first summit 2 or 3 years ago, and we're also very excited for what the future holds. So with that, I'm happy to take any questions.
Any questions for Michael? No?
Could you go into the pros and cons of putting the contracts on, say, the T-chain versus your own chain?
Yeah, absolutely. So the main consideration there is that if you put whatever chain the validator manager lives on needs to be able to produce a valid ICM message from its current, needs to be able to produce a valid ICM message in order to alter the validator set. And what that means is if you put it on your L1 and for whatever reason your L1 halts or you lose control of the validator set or otherwise isn't producing blocks, then it might not be able to produce an ICM message to then reset the validator set. Or to kind of rebootstrap it. So putting it on a chain like the C chain, where you have more stability, if you will, and the validator manager set is much larger, you can have stronger guarantees for the ability to always be able to produce valid ICM messages from the C chain, because those messages are signed by the primary network validator set, even though they're altering your L1's validator manager set. And Yeah, I think the most important step there is really in the bootstrapping, because once you're up and running as a network, hopefully you'd be kind of out of the woods as far as stability and kind of having the sufficient initial validator set size. But that is a real challenge for projects looking to get off the ground. Awesome. I'll be around this afternoon if anyone has any other questions otherwise, but thanks so much for attending.